Alright, so recall that our goal is to prove that geodesics are locally length minimizing. We have shown that it's sufficient to show that radial geodesics are length minimizing. And this is what we are trying to do in the next few videos. In the previous video, we introduced some terminology that we needed for the proof. We introduced for every normal coordinate in the neighborhood radial distance function and the radial vector field. In this video, we're going to discuss the one last ingredient that we need. That is the so-called Gauss Lemma, which says that the radial vector field is orthogonal to geodesic spheres. So let us explain. First, by geodesic spheres, we mean the boundary, these boundary spheres of these geodesic balls. Now, so let's explain concretely what the lemma is saying. Let's say we have a geodesic ball center at P. Let's call it U. Remember, that means that it's the diffeomorphic image of some ball centered at the origin in this tangent space. Now let's take a point Q lying inside this geodesic ball, and then let's look at the geodesic sphere through Q. Recall, so let's see what that means. So Q corresponds to some point up here via that diffeomorphism we just mentioned, right? And so we can look at the circle centered at the origin going through this point in this tangent space. Now the image of that, it's gonna be a geodesic sphere centered at P and going through Q. And sorry, I shouldn't have said circle here. I drew this as a circle, but in general this is a boundary sphere of this disk. Now when we say that this vector field, this radial vector field, is orthogonal to the geodesic sphere, we mean that for each point Q like this vector is going to be orthogonal to the tangent vector of this geodesic sphere. So if we call that x, what we want to show is that the dr at Q is orthogonal to this x under our Riemannian metric. So that means that this inner product is 0. Before explaining the idea of the proof, let us just make some definitions for convenience. Let's say Q is the image under the exponential map of some vector v here. That means if we let gamma v be the unit speed geodesics with initial velocity v, then Q is just gonna be the value of gamma v at the time 1. And from our previous discussion, remember this radial velocity, this is just gonna be the velocity of this curve gamma v, right, at the point Q. So we can also rephrase this is just gamma v dot at the point 1. Alright, so now let's explain the idea of the proof. Well, the key idea here is that we can view this radial geodesics as deformation of gamma in the direction induced by this. So let's see what we mean. What we mean is that they are gonna form a variation of gamma. Recall, by definition of variation, this means that this big gamma at level 0 is our little gamma. And these vectors are just gonna be part of these vector fields along gamma. So let us explain. So let's look at this vector field along gamma. Right, it's capture the change in the t direction. So at the level 0, it's just this velocity vector field of the curve gamma v, right? And so its value at this point 1, that's just gonna be the velocity at Q, which is just this radial vector. And then this vector field captures the change of this family in the s direction, and we'll see that this will correspond to x. But we first have to rigorously define this variation, right? Okay, so we'll do so. And once we do so, the proof comes easily as follows. So we want to show that this inner product is equal to 0. We're going to do so by showing that this inner product is independent of this t. That means that as I move these two vectors along this curve, but staying in this vector field, the inner product doesn't change. In particular, this should be equal to this inner product when t is equal to 0. Now at t equals to 0, this is just the initial velocity vector, this is v. And this vector, the change in the s direction here, that's just 0, because all of this curve has the same initial point. There was no variation in the s direction at P. So then this whole expression must be 0. Alright, so that's the rough idea. Let's prove it now rigorously. So let us first define this variation. Let's construct this variation explicitly.